These are your 7/6 notes on common logs. The reason we call them common logs is that they have base 10, and since our entire number system is based on 10 digits, 0 through 9, and that all of the place values of our number system, the ones place, the tens place, the hundreds, the tenths, the hundredths, and the thousands, is all powers of 10. So our entire number system exists with a base of 10. These type of logs show up in the world. So first thing, when you write a common log, you won't actually see log base 10. It's just sort of awkward. It's sort of understood. And so just like when we write the square root of something, we don't put the little 2 on there, but for every other root we do. So for log base 10, it's not necessary to write the 10 there. It's just understood that you're raising 10. What do you raise 10 to get that number? It's used in everyday formulas. These aren't super important, but sometimes they show up in examples. A pH level of a substance, that determines the acidity of a substance. And so that little scale factor tells you if it's more of like if it's a base or if it's more like an acid. So like tomatoes have a different pH level than like something very much like a base. I can't think of a base right now. pH level of blood is just the acidity of your blood. It measures how acidic your blood is. And so that takes 6.1 plus the log of the bicarbonate in your blood minus the log of the carbonate in your blood. And then back to that pH level of a substance, it's the negative log of however many positive hydrogen ions you have. Loudness can also be used. There's a formula. Loudness is equal to 10 times the common log of R, and R is the relative intensity of that item. So again, I really don't know all of that kind of stuff. That's a little bit more science and physics, but in biology, chemistry, but it's used in real life. That's really the whole main reason I put that up there. So to evaluate common logs, we finally get to use our calculator. In the previous assignment where they gave us that little decimal approximate, we don't have to worry about that because all of these decimal approximates are in our calculator. Someone took the time to evaluate what 10 to the first power is, what 10 to the second is, what 10 to the half is, a quarter, 0.1. And so we can just push a button and we have all of the base 10 logs. So find your log button on your calculator. It's usually along the side of your calculator somewhere. And then just go ahead and type the number, log 6. So to do log 6, you type log and then you type 6, and it gives you 0.7782. We're going to round to 4 places. And so what they're really answering there is what do you raise 10 to get it to equal 6? Well, I know 10 to the first is too big, that's 10, and 10 to the 0 is too small, it's 1. But I know 6 is going to fit somewhere in between there, so it's got to be between 0 and 1. For the log of 0.35, you're going to hit log 0.35, and you get negative 0.4559. Again, if you think about what they're asking here, 10 to the 0 was too big. 10 to the 0 gives me 1. 0.35 is less than 1. 10 to the negative 1 is 1/10, 0.1. So I actually have to even go further and say 10 to the negative second. So it's somewhere between negative 1 and, or 0 and negative 1, which is negative 0.4. Log of a half, if you put in log a half, log 0.5, again, you get a negative number, negative 0.3010. So hopefully, first part of your homework will be pushing buttons, finding it, and using it on your calculator. Okay, the next thing we have to do is solve equations using common logs, and it's actually really easy to do. So these are used when you can't write it as a common base. So let me give you an example. Up to this point, when we had to solve an exponential equation where the exponent, the variable is in the exponent spot, we could simply just rewrite the bases so that they matched. So in this particular case, I'd say 5 to the x is equal to 5 squared, therefore x is equal to 2. But I'm going to show you, what would you do 5 to the x equals 11? You can't write 11 as a power of 5. You can't write 5 as a power of 11. You can't break them down into simpler bases. No matter how you try to do this problem, you can't get common bases. So this is where common logs is another strategy to solve exponential equations. It's another property of equality. Remember, we love those property of equalities. And basically, it's kind of a common sense thing, but if you have two equal sides, if you bring in the log this time, they'll still be equal. Whatever you do to one side and you do it to the other side, they're still going to be balanced. That's the property of equality here. So we've eliminated the log on both sides, but now what we're going to do is we're going to bring in a common log. I have my calculator. I have access to every common log possible, and then I can solve using my common log button. So we're going to not eliminate logs from both sides, but in this example up above, I would actually take the log of base 10 of 5x and set it equal to the log of 11. So that's what we're going to do next. So let's go ahead and try this. I've got 3 to some power is equal to 11. Again, I can't write it as a common base. So what I'm going to do is I'm going to rewrite it as the log of 3 to the x is equal to the common log of 11. Remember, we don't have to write down the little 10. Now, common logs are logs, and so all those properties of logs still apply here. So because I'm taking a log of a base to an exponent or a power, I'm going to drop the power down below, and that's how we get that variable out of the exponent position, and now we can solve using inverse operations. So the very first step is to bring in common logs. The second step then is to bring that exponent down and multiply, change the power to a product. And just remember, this is an ugly decimal and this is an ugly decimal. They're numbers. Remember, when we evaluate that, we're asking what do you raise 10 to get 3? Really ugly decimal. And what do you raise 10 to get 11? Another ugly decimal. So when I'm trying to solve for x, I'm multiplying by an ugly number, so I'm just going to simply divide by that ugly number, log of 3. Whatever I do to one side, I'm going to do to the other side. Okay, it's just like any other solving equation problems. So x, I'm going to put squiggly equal sign. That's approximately. Now I'm going to use my calculator. You got to make sure that you hit equals in between. You don't want to take the log of 11 times the log of 3. So make sure you hit equals after you hit log 11. So if you hit log 11, enter, that gives you 1.0413 divided by log 3, enter. So we get 2.1827 approximately. So again, I don't want to write down those awful decimals. So the longest time that we can, the longer we can keep it in log format and just write log 3, it's so much cleaner and so much more accurate. Let's try the next problem here. So we've got 5 to some power is equal to 62. I can't write 62 as a power of 5, so I'm going to bring in common logs. Log of 5 to the x equals log of 62. So I brought in common logs. I'm going to use the power property to bring down the x. So x times ugly log of 5 is equal to ugly log of 62. To get x by itself, we're multiplying, so now we're going to divide. And when we divide like that, x is approximately, I put log 62 in my calculator, hit enter, divided by log 5, hit enter. I get approximately 2.5643. Now, if you look at your answer, you can kind of estimate. They're asking, what do you raise 5 to get 62? So I got 2 point something. Okay, 5 squared is too small. That was 25. And 5 to the third is too big. So it should be 2 point something, and it is. It's an easy little check to make sure that you're doing them correct. They do get a little bit more complicated here. Okay, so when you have this, I've got this t minus 2 here as the exponent, and then I have another exponent on the other side. So because my variable is on both sides, I'll have to use the power property twice. So bring in common logs, log of 7 to the t minus 2, I'm going to put that in parentheses, is equal to log of 5 to the t. So since the variable's on both sides and it's the exponent, I need to bring that down. So I'm going to use the power property to bring it down. I'll leave it in parentheses since it's a quantity. And then I'm going to bring this one down, t times log of 5. And this gets a little confusing. That log of 7 on the outside of those parentheses is a number. So whenever you have a number sitting on the outside of the parentheses, you can distribute it, and then it has to be multiplied by both things. So you kind of have to make an effort to clean up one side. I have t's on both sides. I could bring over the t minus 2 over to the other side, or I could bring the t over to the t minus 2. I think it's best to try to clean up one side and kind of clean up so that we have all of our stuff in the same spots. So what I need is I need the variables on one side, and if I can, I'd like to get the log on the other. So what I'm going to do is I'm going to bring over the t. I'm going to divide by t. When I divide by t, it comes over here. So now what I have is I have a log of 5. Okay, but a log of 5 is just a number, so I got to get variable and I've got to get number. So I'm going to actually divide by log of 7 as well to make it leave this area and come over here with log of 5. So this is just one great big ugly number. And I think now that things are getting a little crazy, it would be best to switch to decimals. So on the left-hand side, I've got t minus 2 over t is equal to, and then let's go ahead and get a crazy decimal. So log 5 equals, divide by log 7 equals 0.8271. Now I'm going to leave that decimal on there. Now that I have all that, I got to get that t out of the denominator. I guess I should have left t alone, but that's okay. Times by t to get out of here. Now I'm going to put it with this decimal. Now that we have the decimal, it makes a little bit more sense. So now what I have is t take away 2 is equal to this many, 0.8271 t's. So to get how much my t value is, I need to subtract this amount from this 1t and then bring over the 2. So I'm going to subtract 0.8271 t's from the 1t over here, 0.8271, and then I'm going to add 2 to both sides. And so what you get is 1 minus, I'm going to use the answer button to use that decimal. So I've got 0.1729 t's is equal to 2, and then I'm going to divide by 0.1729. I think I actually made this more difficult than it was, not using my strategies correctly. 2 divided by that answer, if you just use the answer button on your calculator, it keeps it accurate, 11.5665, approximately. I think by dividing by t first, though, I probably should have just distributed and taken it from there. All right, we have an inequality. The inequality works the same way as it always did before. So when I do the inequality, I'm going to bring in common logs. Log of 2 to the 7x is greater than log of 3 to the 5x minus 3. Bring down your variable 7x times log of 2, and then bring down your variable using the power property 5x minus 3, that quantity, times log of 3. Do I have my, oh, I forgot to put my greater than symbol in between there. So I think what we want to do is we can distribute the log. Hold on, give me 1 second. Yeah, what I think I want to do here is actually just bring in the decimals. So since this is a decimal, and it's times 7 and it's times x, I'm just going to simplify that whole thing. So I'm going to see how many x's I have here. So I'm going to take log 2, enter, and times that by 7, and now I'm going to actually get 2.1072 x's on the one side is greater than, and then I'm going to actually change these to decimals as well. So I'm going to distribute my log through, and so I get log of 3 make sure you hit enter after that, times 5 is 2.3856x, and then minus log 3 times 3, 1.431. So I think it helps. I tried on the other side to leave them as logs, and I think we just got lost in that. So now that we have these ugly decimals, we can see I'm going to bring the x over to the left-hand side. So I'm going to subtract this x from the one on the left-hand side. In inequalities, I like to put the variable on the left-hand side, so I don't even care if it's negative. So I'm going to type that in, and when I subtract 2.3856, I get a negative 0.2784 is greater than a negative 1.4314, and this is x. So we're going to divide by this ugliness, divide by this ugliness, and so x, when you divide by a negative, flips the inequality, less than. And I have that number in my calculator, so I actually want to divide that number by the last answer. And I get negative 5.1414. And there you have it. Now, when you deal with these, your variable, when you plug it in, it's okay because they're not logs. You brought in the log, but when you plug it into the original problem, it may or may not make the exponent 0 or negative. It's okay because exponents are allowed to be 0 or negative. The last thing we have to talk about in here is anytime you have an ugly base that's not 10, it would be nice if we could actually make it base 10, because then we have the access to our calculator. So the change of base formula is just a formula we use to convert any non-common base, or actually you can use it to create a base of 3 to a base of 4, or a base of 5 to a base of 10. It doesn't really matter. But the most likely way that you'd be changing them is to a common log. So we're going to change these common logs. So I'm going to change log base 3 of 18. And what I'm really asking there is what you raise 3 to get 18. I'm going to say what you raise 10 to get some other number, and they'll be equivalent. The formula itself is a little confusing, but it's not that bad. Write it down. Log base A of n, that's the original, is equal to log base B of n, so B is the desired base, over log base B of A. So you take the original value here, the original base, and that's going to go in the denominator. The original thing that you take in the log of goes in the numerator. And then you're dividing by the common log, or whatever log is desired. So in this case, I'm going to take the log, common log of 18, and divide it by the common log of 3. And what that gives me, log of 18 divided by log of 3, it gives me 2.6309. And you could check your answer by seeing, do you raise 3 to the 2.6309, and does it give you 18? That's what we're asking. For the next one, log base 7 of 5 is going to become log of 5 over log of 7. Log of the number, log of the number over log of the base. And so you do log of 5 divided by log of 7, and you get approximately 0.82701, or 71. And that's what you'd raise 7 to get 5. The last one, log of 0.45 over the log of 2. So then we can use our calculator from there. I'm not worried about that one. So your lesson summary, I want you to use a change of base formula to change log base 4 of 3 to a common log. Show your work, show the fraction and the work. And then I want you to actually solve that common log, or using common logs. Good luck.